Okay, so now what we'll have will be the solutions for activity A, which is all about thermochemistry. This activity has three problems. One with regards to heat. The second one, it's very similar to a calorimetry problem. And the third one, it's an enthalpy problem, which involves phase change. What we will be doing is I will be solving them one at a time. Also, um, a document file or a PDF file will be sent to you accompanying this video. Okay, let's start with the first one. Okay. So the problem says copper wires used to transport electrical current heat up because of the resistance in the wire. If a 140 grams wire gains 280 joules of heat, what is the change in temperature in the wire? Copper has a specific heat of 0.364 joules per gram degree Celsius. Okay. So let's just get my pointer. So the technique here is to really, at the onset of the problem, or when you start solving the problem, is to get the given. So let's check. We can see that we have 140 grams. We also have 200 joules of heat. And there is a specific heat of 0.364. So let's just write those data. So given, we have mass. It's good that you list down the given that you see in the problem, because it would guide you on, first, of course, what is missing. Also, you would see consistencies or inconsistencies in units. So if there should be conversions that you need to do, then you can do them. So I'm sorry, I'm writing as I'm speaking. So mass, that's 140 grams. And then we have 280 joules of heat. That's a Q. And then another value that we see is specific heat. So that's C, which is 0.364 joule per gram degree Celsius. Okay. So it's quite obvious what formula we'll be using, because we have M, we have Q, we have C. And what are we looking for? The change in temperature. I remember from our discussion that when I say change in temperature, that's always a delta. It's a difference between two temperatures. So that is what we're looking for. So what I'm going to do now is, of course, just use the formula for heat. We have Q equals MC delta T. So we're looking for delta T. We can just say that delta T equals Q all over MC. So that is, you can check the units. The units are already consistent. For the specific heat, you have a joule per gram degree Celsius. For the mass, that's a gram. And then for the heat that is given, it's already joules, so no need for conversions in between. So all you have to do is directly substitute the formula. So Q is 280 joules all over. This is 140 grams. And then we have for C, that's 0.364 joule per gram degree Celsius. Okay. In this case, where is this coming from? Some might be curious. For example, it's not given in the problem. You can actually get this from a table of constants. If it's not given in the problem, then probably you could refer to a reference with the constants. So just using, of course, your calculator, you can get the answer that we'll be getting here. I'm sorry, why is that a Q? Let me just erase that. Okay. Okay. Let's get the pointer again. So we're getting, sorry for that, delta T equals, I got a 5.49 degrees Celsius. Probably there would be variations, slight variations in the values that we will be getting because of the constants. But in this case, this should be exact because I did not use another constant. I used what was given in the problem. So going back, before we go to the next one, first thing to do, list what is given in the problems. You have mass, you have heat, you have specific heat, and then go ahead and look for a formula wherein you can get what is missing, which is change in temperature. And we know that we will be using the Q equals MC delta T formula. And then all you have to do is, of course, manipulate that formula and you're getting delta T equals Q over MC. And then it's a direct substitution of values. And then you're getting 5.49 degrees Celsius. Okay, this is your answer. If we're doing this in a quiz or another activity, make sure that you indicate your final answer. Okay, that's our problem number 1. Now for problem number 2, this is, I believe, a calorimetry problem because what we're doing is analyzing the heat transfers in substances. So let's just read the problem. It says 240-gram piece of copper is dropped into 390 ml of water at 22.6 degrees Celsius. The final temperature of water was measured as 39.9 degrees Celsius. Find the initial temperature of the piece of copper. Assume that all heat transfer occurs between the copper and the water. So it's also using the principle of the first one, thermodynamics. It's a closed system wherein heat transfer, there's total heat transfer occurring between copper and water. So what you'll be doing here is to get the two sets of data, the data for copper and the data for water. And then, of course, the usual, get your heat capacity formula and then just compare them. Okay, let's first list the given. So I said a while ago, you have to get the data for copper and water. So what you can do is, of course, this is up to you. This is not like, this is a must, like you should do it in a table or something like that. Just make sure that you identify which data is for copper and which data is for water. So in this case, copper, we have mass, which is 248 grams. And then we also have, we're looking for the initial temperature per piece of copper. So we don't have a delta T here right away, but we have a final temperature because you can look and check the statement. It says the final temperature of water was measured at 39.9, meaning both water and copper has a final temperature of 39.9. So we get here, or we write here 39.9 degrees Celsius. And then now this is an example of a problem wherein there is no given data for constants. So you refer to the table that was given to you. So if you wait, let me just check. Oh no, okay, let me just do that. Let's go back to that. There's a table that was given, which is here, which is the specific heat and molar capacities. It's this one. And I believe I gave you another table. So you can just refer to the tables that were given. So I go back to the presentation. Just validate or just verify from your tables, your table of constants, if what I'm using is the correct constant or not. But of course, I'm using the correct constant. So for copper, the specific heat of copper is 0. From the table that was attached with the activity, joule per gram degrees Celsius. And then we also have for water, we have another set of data for water. It says that mass is 390 ml, which is, of course, we can say that that's 300 grams. And then we have initial temperature here. We have T1 equals 22.6 degrees Celsius. We also have, of course, the same final temperature, which is 39.9. And of course, we also know that from the table, you know that the sea of water, remember, there are different C's for water depending on its state, but for liquid water, it's 4.186 joule per gram degrees Celsius. I'm getting this from that table, not from the second table that I passed to you in FB or in the group chat. This is coming from the attached table. I'm using the data or the constants from that table. But for example, what you used was the table that was given with the sea of waters 4.18. That's okay. I'm giving tolerances for the final answers. So in this case, what I can do is I can use the formula in calorimetry or for calorimetry, which is Q gained equals negative Q loss, because it says all heat transfer. That's like an indication that this is a heat transfer formula using the conservation of energy concept, wherein there is no heat loss in the system. So Q loss. Now, I remember I was telling you that even if you interchange, which is Q gain, which is Q loss, as long as one is negative, then it would still give you, or it would help you arrive with the correct answer. For this problem, what I'm assuming would be Q gain will be the substance that heat up, and Q lost will be the substance that cooled down, because it's the one that is releasing heat. So let's continue. So I'm saying again, I have just rewrite those. Q gain, equals negative Q lost. For me, which gained temperature? For me, the one which gained temperature is actually water, because as you can see from the problem, if you go back, it says here that the final temperature of the water was measured at 39.9. There's an increase in temperature. The initial temperature of water was 22.6. It was actually colder. So what you do is, I'm assuming that the one that lost, or the one that gained is water. So I'm putting here Q of H2O negative Q of copper. Okay, and in problems like this, that's again a Q, and we have a generic formula for Q, which is MC delta T. So this is MC delta T. It's also equal to negative MC delta T. This is up to this point. If you get the analysis up to this point, the chances of you getting the correct answer is already big, unless, of course, there should be errors in inputting the values in the calculator. But I'm doing this the long method so that you can see it also. So I'm gonna plug in the values for water, which is the mass of water is 390. And then the C of water from the table is 4.186. And then the delta T, I said that the one that heat up is water. So from 39, it went up to 39.9 from 22.6. So that is my first equation. On the right side should be the data for copper. So I'll attach the negative sign and of course input the different values. The mass of copper from the problem is 248. And then the C of copper is 0.386. And then in this case, I don't know the initial temperature of copper, but I know the final temperature. And for me, what I'm getting here is supposed to be higher than 39.9, because I said that it is copper which cooled down. So there you go. So we're looking for T1. So all in next is of course manipulation, just your calculator. But as I've said a while ago, I'm doing this the long method. So this is 390. There could be differences in our decimal places, but that counts for the constants that I used or that you used. Okay, so that's the difference here, 17.3 equals, I'm distributing this. So this is 248 times 0.386 times 39.9. So that is actually a negative 3819.55. I'm doing it the long method. I'm not using shift solve or anything. Okay, minus. But since that's a, this is a negative sign, so this is negative, and that becomes positive because negative, negative, plus 95.73 T1. You might be asking where I'm getting that. That's 248 times 0.386. That's actually 95.73. And then negative times negative, that's a positive. So therefore, computing it in your calculators, the answer is 334.93 degrees Celsius. Or if you're getting values which are near 335 degrees Celsius, I'm going to accept them. So that is the initial temperature of copper. Okay. Okay, these are the answers. Okay, if you're getting like 334 point something, as long as it's around 334 to 335, I'm going to check your answers in your activity. Okay? So just go back to this video if you need to validate your answers again. So the last one, this is the classic enthalpy problem wherein it involves phase changes. It's from ice to steam. So we had one like this in our sync class and also on the YT videos that were uploaded beforehand. And this is very similar, but I'm gonna redo it so that it's more clear and you can actually do it with mastery already. So this is an ice to steam problem. So this is ice to steam. And as I've said during our discussion, ice to steam doesn't like automatically becomes ice to steam, and it has to go through different stages. And when there are changes in temperature, you will be using the MC delta T formula, and when there are phase changes, you have to use HF or HV. So let's first get what's given in the problem we have here. That's mass, which is 1.7 grams. We also have initial temperature of negative 12, which is actually the temperature of ice. How important is that? Because it actually starts your analysis in getting the different heats per stage. So if you miss the temperature, and say you have an error in the sign, then it follows that your final answer might be affected. So be careful in listing down whatever is given in the problem. So we also know that steam at the end point or the last stage, it's given 105 degrees Celsius. Also, I'm writing the different constants already. So we have C of water. I'm mixing two tables now because the tables that were given for this activity were incomplete. And then we have C of ice. This is what I've been telling you, even if you know that this is of course just solid water, and then that's liquid water, and then it's water in vapor state. It still has different C's, of course. C of steam, it's 2. You might find data wherein C of ice is 2.11, then C of water is 4.8, and that's okay. But we will still have near answers, or the values of our answers are still near. And then we don't have values for heat of fusion and heat of vaporization from the table, so I'm giving them. Heat of fusion is 334 joule per gram. And we have heat of vaporization to be 2258 joule per gram. Okay, this is what usually, this is the usual way I solve problems. I list all given so that it's easier to plot them in the different equations, especially this is a first stage computation. So the initial stage is actually Q1, wherein, of course, it's ice to, you have to bring ice to its freezing point because it's at negative 12. So you have to bring it to 0, which is the freezing point of water. Okay, where were we? So we're on that stage. We're in, I'm sorry, I had to stop. I just had to check on something. So the first stage is actually ice to ice. I was telling you that you have to bring the negative 12 degrees ice to the freezing point, which is 0. So when there's a change in temperature, by the statement itself, you're bringing ice to a 0 degree Celsius. So that's an MC delta T. So you do MC delta T. So here, it's not really a problem because even if it's in liquid form, in solid form, in steam form, it's going to use only one mass. So this is 1.7 grams. And then here, remember, this is still in ice state. But it only has change in temperature. So the C of ice, we'll be using C of ice, which is 2.05. And then you're bringing it to 0. So that's 0 minus negative 12. Sometimes that leads to the confusion why in the equation it's positive 12 because of course minus minus, that's already a positive. So this is 1.7 times 2.05 times positive 12. So again, where is that coming from? You're bringing it to 0 from negative 12. So your final temperature is 0 and your initial temperature is negative 12. That's why this is a positive 12. So Q1 here now is 41.82 joules. Okay, that is the first stage. Now we're getting Q2. Now you've already brought that ice to the 0 degrees, which means it's still ice. Now you have to change it to liquid water. So in changing it to liquid water, you have to, of course, use fusion there. I know its fusion is more on liquid to solid, but of course, the heat that is involved is what you call the heat of fusion. So all you have to do here is use delta HF. So this is just very easy. So that's 1.7, sorry, what was that? 1.7 times delta HF, which is 334. You can actually cancel the grams because it's joule per gram, and then this is also grams. So all you have to do is multiply that. We're getting Q2 at 567.8 joules. Again, don't worry if you've used different constants. Let's say you're using 2.11 and 4.18. I don't mind. I'll be the one adjusting when I'm checking your seat works. Okay, now let's go to Q3. Q3 is still the same. Now, it's now in liquid form. It's now in liquid water form, but it is at 0 degrees Celsius. So you have to bring it to boil to make it steam. So you have to bring it to a temperature of 100 degrees Celsius. So that's an MC delta T. Okay, so M again is 1.7. Now, this is now in water form. It's liquid water. So you're using the C of water, which is 4.186. And then delta T, you're bringing it to 100. So your final temperature is 100. So let's put that so that you will see 100 from 0. So now Q3 here is 711.62 joules. Okay, Q4. Now it's already water at 100 degrees, but it has to change its state because our target is to be steam at a certain temperature. So you have to change this liquid water to steam. But since here already brought it 100 degrees, it's already boiling, but it's not yet in vapor form, or it's not yet in steam form. So what you need to do is introduce the heat of vaporization. So this is 1.7, and then you use the HV, which is 2258. So Q4 now is equal to 3838.6 joules. And finally, for Q5, it's already steam at this point, but I have to bring it to 105 degrees Celsius. So that is again an MC delta T. Remember, those are like checkpoints. Those are words that you can, remember. Bring it to a temperature of. You have to increase the temperature to. You have to bring the temperature down to. So you can really see that there are changes in temperature. So this is an MC delta T, so that's 1.7. Now for C here, you're using the C of steam, which is 2. And then delta T, it's 105. Your target is 105 degrees Celsius, so 105 minus 100. Because at this stage, it's already at 100. Now, all you have to do is bring it to the final temperature of 105 degrees. So your Q5 here is 17 joules. And of course, the problem says that you have to get the total energy required to convert ice to steam. All you have to do is add all. So Qt now is equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. And of course, your calculator magic, you're getting, okay, I'm going to list them down so that you can still check your answers. 567.8 plus 7, oops, sorry, what's that? It's not writing. Okay, 711.62 plus 3838.6 plus 17. And your final answer is 5176.84 joules. So that's your total Q. So that's the total heat required to convert that amount of ice to steam at 105 degrees Celsius. Okay. So those are the solutions for the 3 problems in the activity. I hope this helps you in reviewing or in validating your answers for activity. So just save this or bookmark this, and then you can always use it for your review. Okay, so that'll be it. So we'll now go to our next lesson. Okay, thank you.